to give a survey of Sasha Borishev's work on geometric properties of reproducing kernels in Hilbert spaces of analytic, actually mainly entire functions. Of course, this is only a small part of deep and beautiful results of Sasha, but this is the part which I'm more familiar with, and moreover, I was very lucky to be able to collaborate with Sasha on some of the problems about which I plan to talk today. So if we are given a Hilbert space, reproducing kernel Hilbert space of functions, analytic in some domain, and if we want to study this space, then one of the basic questions we need to answer is the structure of the sampling and interpolating sequences in this space. Let me recall the definitions. We say that a sequence of points is sampling sequence for the space if we can compute the norm of the function in this space as such a weighted sum using the samples, the values of the function, these points with some weights. These weights, which depend on the norms of the reproducing kernels, they are natural and unavoidable in this problem. And a sequence is said to be interpolating if we can interpolate any L2 values at these points lambda n, again with some weights, and the weights are again the norms of reproducing kernels. And finally, if such function f is unique, the solution of the interpolating problem, then we say that lambda n is a complete interpolating sequence. And equivalently, a complete interpolating sequence is a sequence which is both interpolating and sampling at the same time. And it is well known that these properties can be transformed to geometric properties of corresponding systems of reproducing kernels. For example, lambda n is a sampling sequence. It simply means, by definition, that normalized reproducing kernels form a frame in the space. And lambda n is interpolating sequence. It means that normalized reproducing kernels, they form a Riesz sequence, that is, Riesz bases in their span. And finally, complete interpolating sequences, they correspond to normalized Riesz bases of reproducing kernels. Of course, there are many spaces of analytic functions which do not have Riesz bases of reproducing kernels, which even do not have frames of reproducing kernels sometimes. But today I will speak about good situations when such systems exist. So one of the main objects of my talk will be the Fock type space. So assume that we have some function phi, which grows faster than the logarithm to exclude the non-interesting finite dimensional case. And we consider the set of functions, analytic entire functions, which are square summable with this weight over the whole complex plane. And the classical Bargmann-Segal-Fock space, it corresponds to the case of a quadratic function phi. So the functions which are square summable with the Gaussian weight over the plane. And in this case, the reproducing kernels, we even can compute them explicitly. They have very simple form. They are usual complex exponentials. And so if you're given a Fock type space, then there are natural questions to describe sampling and interpolating sequences for this space. And also one can ask whether there exist complete interpolating sequences, Fock type space, that is Riesz basis of normalized reproducing kernels. And the first fundamental result of this problem was the solution by Sape and Walston of sampling and interpolation in the classical Fock space. They give a description in terms of certain densities, and in particular, it follows from this description that there are no complete interpolating sequences in the classical Fock space. Then this result was extended by Marco Massaneda and Ortega-Cerda for the case when the function phi is subharmonic and delta phi, its Laplacian, is a doubling measure. For example, this covers the case when phi of r grows as a power function. Phi of r is r to some power alpha positive. But it turned out that a similar description is possible for a much larger class of weights, for weights which grows faster. And this was proved in 2007 by Borichev, Duez, and Kellet. They covered a wide range of growing weights. But in all these three situations, the description was given in terms of some densities. I will present the exact formulation on the next slide. And each time it was clear that there are no complete interpolating sequences because there were some strict inequalities for upper density, lower density, which never meet. And so in all these cases, there are no complete interpolating sequences in the corresponding Fock type space. And in 2010, Sasha and Yura Lubarsky produced first examples of Fock type spaces which have complete interpolating sequences. And moreover, they found a sharp border for this phenomenon. So let me now pass to the exact formulations. In the study of Fock type spaces, a very important role is played by the Laplacian of this function, phi, and rather Laplacian to the power minus 1/2, this function which I denote rho here. And if phi is a smooth function, then it's simply can be computed like this. And let me mention that, for example, if we are in the classical Fock space, then this function rho is constant. And if, roughly speaking, if phi grows faster than r squared, then this rho tends to 0. And if phi grows slower than r squared, then this rho tends to infinity. And this rho induces a certain metric on the plane, and I would say that the sequence lambda is rho separated if the corresponding infimum for all different points is positive. And also we consider two densities, up and lower Berger-Landau densities, which are again depend, of course, on this parameter function rho, and they defined as follows. So we consider the number of points in such a disk, and we take the infimum or lower limit when z tends to infinity for fixed r, and finally we divide by r squared, essentially by the area of the disk, and consider the lower limit as r tends to infinity. And similarly, we define the upper density. And now I can state the result by Borichev, Duess, and Kelly. So assume now that rho decreases to 0 at infinity, which means that we are in the case when phi grows faster than r squared. And also an additional condition that rho prime times log 1 over rho also tends to 0 when r tends to infinity. Then the set lambda is sampling for the corresponding Fock space if and only if it contains a rho-separated set lambda prime with lower density strictly greater than 1/2. And the set lambda is interpolating for the Fock space if and only if it is itself rho-separated and its upper density is strictly less than 1/2. So this coincides with the result of Sape and Walston for the classical Fock space. This is exactly the same densities, exactly the same conditions. But now it's clear from this description that there are no complete interpolating sequences for all such spaces. So here I simply repeat the formulation of this theorem, and I would just want to mention that it applies to the cases, for example, r to the power alpha when alpha is strictly greater than 2, but also phi of r can be exponent of r or even something growing to infinity even faster. So there are quite a lot of different weights which are covered. So there are no upper bounds, so to say, for the growth of the weight in this theorem. It can grow to infinity arbitrarily fast. Also, all these results, I formulate them for Hilbert space case, but they are true for the whole LP scale of Fock spaces, and analogous results were obtained in the same paper for the Bergman spaces in the disk. And I would like also mention one more paper by Sasha with Andreas Hartmann, Karim Kile, and Shavima Saneda, which studies sampling and interpolation with unbounded multiplicities now in the classical Fock space. And they showed in particular that there are no sequences which are simultaneously sampling and interpolating when these multiplicities tend to infinity. So again, there are no complete interpolating sequences, even if we allow multiplicities. So, but now let us pass to the case when complete interpolating sequences do exist. So in 2010, Borishev and Lubarsky produced the first examples of such situation. And they give a very concrete example of such spaces. Assume that phi of r, our weight function, is logarithm of r to the power beta when beta is between 1 and 2. 1 is not included. In this case, there exist complete interpolating sequences, or in other words, there is basis of normalized reproducing kernels in the corresponding Fock type space. And let me recall that if we consider this function rho, this plus to the power minus 1/2, then for classical Fock, it's constant. And for the function phi of r, which is log r squared, this rho is constant times r. So it has such fast growth. And one more result by Borishev and Lubarsky, it shows that why this log r squared is the sharp bound of this phenomenon. They prove the following. If rho of r is O small of r, which means that phi grows faster than this log squared, plus some additional regularity conditions, which I will not present some, then there are no complete interpolating sequences in the corresponding Fock type spaces. So this log r squared is in a sense a sharp bound for this. There were some further developments, some further results in this direction. So Borishev proved in 2017 the following. Let us now introduce new function psi, which is of t, which is phi of exponent of t. So for our logarithmic function, this psi is again a quadratic function. And if the second derivative of psi tends to infinity, and it's non-decreasing, then there are no complete interpolating sequences. While if the second derivative is non-increasing plus some additional regularity, then there exist complete interpolating sequences. And there were also a series of work by Isaev and Gulmuhametov, who started similar problem and somewhat improved this result. In particular, they showed the following, that if psi is sufficiently regular, there are always some regularity assumed, and it is essential that without it, one cannot obtain, and the result even is not true, but there are some technical conditions which I do not present. So they show that if psi is sufficiently regular, then complete interpolating sequences exist if and only if the second derivative is bounded. So all these results, they show that this log square is indeed the exact sharp border of the situation when we have complete interpolating sequences. Okay. But these results were about existence. And now I want to say a few words about description of complete interpolating sequences. So consider this case of logarithm squared. Consider this, we call it small Fock space, because actually it's a space of functions which grow very, very slowly in the have zero order. So it's indeed a very, very small space. You can see comparing with the classical Barkman Fock space, for example. And in 2015, jointly with Dumont, Hartmann, and Keller, we obtained a description of complete interpolating sequences, which I want to present now. So in the paper of Borishev and Lubarsky, they constructed explicitly, in this case, this complete interpolating sequence. It was simply given with this normalization of the weight by exponent to the power n, this exponential system. Now we will give a criterion in terms of deviations from this complete interpolating sequence. So assume that we have sequence lambda n, which are ordered by an increase of the moduli, and we write lambda n as e to the power n, exponent of delta n, so it's a deviation of the modulus, so to say, and the argument. And now lambda n is a complete interpolating sequence for this small Fock space, if and only if first lambda n is separated, which separation means in this case this thing, so more or less exponentially separated. Second condition, delta n, these deviations must be bounded. Moreover, these deviations actually must be small, but they need not be small individually. They must be small in the mean, so to say. And this is my last main condition, is that if we take such sums, such means of this delta k over sufficiently large intervals, and divide the length of this interval, and take the supremum over all such shifted intervals, this supremum must be strictly less than 1/2. So in this case, it is possible to describe complete interpolating sequences looking simply on the deviations from this initial complete interpolating sequence found by Borichev and Lubarsky. This condition, it resembles a bit of Donion's condition in the theory of these bases of exponentials in the interval. But there, of course, it's only a sufficient condition. And here it's necessary and sufficient. So this was the complete description of such complete interpolating sequences in this space. And let me also mention very briefly some further developments in this direction. First of all, Kelly and Omari described complete interpolating sequences for other cases from the paper of Borichev and Lubarsky. So we have log r to the power beta when beta is between 1 and 2. And also Omari described complete interpolating sequences for the log square weight, but in the all LP scale of Fock spaces. And it turned out that there is some interesting dependence on this exponent p, rather non-trivial. And one more result which I want to mention is an application of this Fox type space and description of its complete interpolating sequences to the time frequency analysis, to description of complete interpolating sequences in the shift invariant spaces generated by the Gaussian or the second type functions. And so it has some applications to Gabar frames here. I recall the definition of the shift invariant space. This is a space of functions on the real in L2, subspace of L2, which is generated by shifts of some fixed function. I'm not going to go into detail here, but still I want to mention that this space with phi of r, which is log r squared, which looked as a sort of a bit rather toy example, maybe in the beginning, but it turned out to be very useful and appears naturally in some completely different problems. And this existence of these complete interpolating sequences, it turned out to be very useful in the time frequency analysis, and worked on this with Yuri Belov and Karl-Heinz Grechenik, and in particular obtained a complete description of complete interpolating sequences in this setting. Well, okay, so I think now I will move to another question, another group of results, which is related to the notion of so-called hereditary completeness. So before we were talking about frames or even these bases, which give us some very good ways to reconstruct a function, expand it into a series of, with respect to this system. But there are, of course, much weaker reconstruction, variants of reconstruction, variants of expansion, and one of them is related to this notion of hereditary completeness. So let me give the definition. Assume that we are given a complete and minimal system of vectors in a separable Hilbert space, and that Yn be its orthogonal system. And then we say that the system Xn is hereditarily complete if for any vector x in H, x belongs to the closed linear span of the terms of its Fourier series, or the span of the partial sums of its Fourier series with respect to the this orthogonal pair. So by Fourier series, I mean such a formal series like this. We compute coefficients, taking the inner products with Yn, and we take them as coefficients at Xn. And this property, it can maybe understood as the weakest form of the reconstruction of a vector from its formal Fourier series. It simply can be approximated by some linear combination of its partial sums. Equivalent definition is that for any partition of the set of the indices M, if you consider the mixed system, which we take part of the initial system and part of the orthogonal system, we will call such object a mixed system. And for such a mixed system must be complete for any partition of the index set. And such theoretically complete systems, they are also known under several other names. And sometimes they're called Strong-Markushevich bases, and sometimes one speaks about them as systems admitting spectral synthesis, and this comes from their relation with the spectral synthesis problem for invariant subspaces of linear operators, by results of Marcus and Nikolsky, but this I will not discuss here. So, and arguably one of the major themes of 20th century harmonic analysis is the study of geometric properties of complex exponentials in L2 on an interval. So they give lambda and some complex numbers. We consider the corresponding systems of exponentials. And then there are many natural questions like when such a system is complete, when such a system forms a Riesz basis, when such a system is a frame, etc. And here I mentioned some milestones, some very important results, and some names. First, there is Berlin Maria Venn theorem about radius of completeness for the completeness problem, and description of Riesz basis by Pavlov, Khrushchev, and Nikolsky. Well, and one can also ask, if we are given a complete and minimal system of exponentials on an interval, whether such a system will be hereditarily complete. Of course, this is not, this problem is not so well known as the other, but still it was a question which specialists were interested in. And in 2013, jointly with Sasha and Yuri Belov, we obtained a solution of this problem, which I would like to show. So assume that we have a complete and minimal system of exponentials, to on an interval, that the tilde is the orthogonal system. This orthogonal system is automatically complete. It's an old theorem by Young. And our result is as follows. First of all, in general, the answer is negative. There exist complete and minimal systems of exponentials which do not admit spectral synthesis, which are not hereditarily complete, which means that there exist functions which we cannot approximate, cannot reconstruct, looking at the corresponding generalized Fourier series. For example, there is no linear summation method for such a non-harmonic Fourier series. But there is also some positive result, namely, for any partition of the set lambda, if you consider the corresponding mixed system, it has defect, that is the dimension of its orthogonal complement, is always at most 1. So unless we can approximate everything up to dimension 1. So that was our result. And well, formally speaking, it's about exponentials, but of course, this is also a result about reproducing kernels. Actually, that's how it was proved. Of course, we need to pass to the setting of spaces of entire functions, namely to the Peli-Wiener space via the Fourier transform. In this case, the exponentials, they are mapped to cardinal sign functions, which are reproducing kernels of the Peli-Wiener space. And then for the reproducing kernels of the Peli-Wiener space, we have the same property that complete and minimal system need not be hereditarily complete, but the defect is always at most 1. So that was the result for the Peli-Wiener space. And then we looked at a more general class of spaces, which are the so-called de Branch spaces of entire functions. This is a class of functions which generalizes the Peli-Wiener spaces. and it appears in the branch theory of canonical systems. And well, there exist many ways to define the branch spaces, and it's all rather technical, and I'm not going to spend much time on this. One of the ways one can think about the branch spaces, essentially spaces of discrete Cauchy transforms of some measures on the discrete measures on the line. So functions which can be represented like this, where t is a sequence tending to infinity, mu is some masses with this condition. And essentially this pair set t and the measure mu, this masses mu n, they more or less describe uniquely the structure of the space. Well, here is a simple example that we prepare the Wiener space. It corresponds, of course, to the case when t is integers, masses are 1, and in this case, this representation is a Cauchy discrete Cauchy transform is simply the classical sampling formula by Shed and Kotelnikov with Becker, etc. So it's a class of quite interesting spaces with rather rich structure and interesting connections to other problems. And we studied a problem about spectral synthesis, hereditary completeness of systems of reproducing kernels in this space. And in particular, we show that in this case, one can have systems with any given finite or infinite defect. So in general, the spectral synthesis problem has negative solution again. But also we obtained an explicit description of the branch spaces where any complete and minimal system of reproducing kernels is automatically hereditarily complete. And it turned out that these are the branch spaces which coincide with the appearance of norms with some radial Fock type space. And all such spaces, they are of very slow growth. Again, here appears this growth as this log R squared. It appears again. And why this problem in the branch spaces is of certain interest, this is because it can be applied to the spectral theory of rank 1 perturbations of complex self-adjoint operators, because there is some functional model that we developed with Dmitry Kubovich for such rank 1 perturbations, model in the branch spaces. And questions about reproducing kernels, they are exactly the questions about the eigenvectors of the corresponding rank 1 perturbation. And now I will return back to the case of the Fock space. Now it will be again the classical Fock space with Gaussian weight with this normalization with constant pi here. And one can, of course, ask the same question for the Fock space. If I given a sequence of reproducing kernels, complete and minimal, whether it will be hereditarily complete or not. So assume that we are given a complete and minimal system of reproducing kernels. Let G lambda be its orthogonal system. The orthogonal system can be obtained in a very simple way from one generating function G lambda. It can be divided like this. And the system will be orthogonal to a complete and minimal system of reproducing kernels in the Fock space. It is always complete. It was proved in the classical case by Yuri Belov. And for it, then it was extended to a wide class of weighted Fock spaces. In every Fock space, Isidore Fock space, the orthogonal system is automatically complete. And what about hereditarily completeness? Hereditary completeness, then? It turned out that the answer is completely the same as in the Peri-Wiener space, even if the Fock space and the Peri-Wiener space, they are very different in many, many respects. They are very different spaces. But the answer is the same. There exist complete and minimal systems of reproducing kernels in the Fock space, which are not hereditarily complete. However, the defect of any such mixed system is always at most 1. So either it is 0, either it is 1. So that was the solution of this problem for the Fock type space. Okay. And now also this result can be applied or have relations to the time frequency analysis and Gabor systems generated by the Gaussian. So assume that let me recall that we have a function g in L2 on the line. What are its time frequency shifts? We shift and also we multiply by this exponent. And then we can construct, if we given some set lambda, subset of complex plane, then we can consider the Gaber system, which is the set of this time frequency shifts where x plus iy belongs to lambda. Well, usually this lambda is assumed to be some sort of lattice, but in general, it's not necessary. It is not necessarily lattice. And so if we consider the function g to be the Gaussian, then the Bargmann transform maps L2 on the line unitarily onto the Fock space, and the time frequency shifts of the Gaussian are mapped to the normalized reproducing kernels of the Fock space. And so the results that we had for the reproducing kernels of the Fock space for the usual exponentials, it also gives a result about time frequency shifts of the Gaussian. So there exist non-hereditarily complete Gaber systems. But again, the defect is always at most one. So one consequence of our proof of the construction of a non-hereditarily complete system in the classical Fock space is that there exists a function g in F such that it's not only in Fock space itself, we can multiply it by any polynomial and it's still in the space. Well, and so there exists such a function g such that the set of the functions which are divisible by g and which belong to the Fock, this is Fock space F, it does not coincide with the closed linear span of the polynomials times g. So there exists a function f such that fg in the Fock space and fg is not approximated well by the function of the form polynomial times g. So it's a weighted polynomial approximation in the Fock space. And this example, it is related to a very interesting old problem by Newman and Shapira in 1966. And assume that g is a function in the Fock space, and now we can multiply it not only by polynomials, but by any exponential for any complex number w. We can multiply, and we are still in the Fock space. And Newman and Shapira, they asked the same question: is it true that the closed linear span of such exponentials times g coincides with simply the set of all functions which are, so to say, divisible by this function g in the Fock space? And actually, this problem is related, why Newman and Shapira were interested in this, it is related to description of the adjoint of the operator of multiplication by g in F. It's an unbounded operator. And if we're interested in the structure of its adjoint, then the question is closely related to this approximation problem. And the question about the adjoint of the multiplication operator, it was posed by Fisher already in 1970, more than 100 years ago. And so the last wonderful result of Sasha, which I would like to discuss, it's the solution of this problem by Newman and Shapira. So this 50 or maybe even 100-year-old problem, it was solved by Sasha jointly with Yuri Belov in 2018, and last year the proof appeared in Journal of European Mathematical Society. So let me now discuss these results. So first of all, again, in general, the answer is no. The solution is negative. It's not, in general, it's not true. Even it's not true in some much stronger sense. Namely, the result is as follows. For any alpha between 1 and 2, there exist entire functions f and g, such that f, g, of course, also gf, all of them are in the Fock space. And moreover, g can be multiplied not only by exponentials, it can be multiplied by any function h of order at most alpha. And still this product is in G, is in F. So G is actually a function in the Fock space, which is much smaller than the critical growth, so to say. We can multiply it by any function of some order at most, or at most alpha. But still, the function GF cannot be approximated by the function of the form linear combinations of such functions, exponentials times G, or polynomials times G. These two spans actually coincide in this case, these polynomials and exponentials, but anyway, the function GF is not in this linear span, and this gives the negative solution for the problem of Newman and Shapira. And interestingly, this construction of the counterexample is based on an earlier work by Sasha from 1998 about polynomial approximation in Fock-type spaces. And these results turned out to be very useful here to construct this example. But also, there are some positive results in this Newman-Shapira problem. Let me show them. So assume now that the function G is a function of completely regular growth. I will not give the exact definition, but essentially it means that outside some small exceptional set, G grows as is prescribed by its indicated diagrams. And so assume that G is of completely regular growth, and assume that it is of type, with respect to order 2, strictly less than pi over 2. Pi over 2 is, of course, the sharp estimate for the type, the function in the Fock space. They can have type with respect to order 2 at most pi over 2. But we now assume that the type is strictly less than pi over 2. And we assume some additional regularity of zeros, some technical conditions, which I will not present here. But then in this case, the answer to the Newman-Shapira question is positive. Then indeed, any function of the form fg is in this span. Well, and another result, where one doesn't assume any additional regularity of zeros. But in this case, one have to assume some much smaller growth. Maybe assume again that GO is of completely regular growth, and assume that its zero set has the upper density less than 1 over pi. The upper density is defined like this. Again, we count the number of points in the disk divided by the area of the disk. And for our Fock space with this normalization, the critical density is 1 actually. And here we assume that the density is less than 1 over pi, so it's much smaller. But then in this case, again, the Newman-Shapira problem has positive solution, and again, these two sets coincide. Okay, I think it's time to stop here. So in conclusion, I want to thank Sasha for the beautiful mathematics he introduced me to. So thank you very much for your attention.